Hello everyone, welcome back to Office Hours with Zach. I'm very happy to be here today, and I'm here to answer a very important question that we got from a viewer about the placement of ground near traces in the PCB. How does it affect EMI and EMC? How does it affect signal integrity? I'm going to break this down and answer these questions right now. Let's go ahead and get started. So before we jump onto the whiteboard, let's take a look at that viewer question. Albert Ray 3424 writes, for better SI and EMC, is it better to have a ground plane as close as possible to the signal layer? Doesn't this increase the rise time since the capacitance of the transmission line increases too? If so, isn't this a bad move for high-speed links? Seems counterintuitive since signal ground layer pair is recommended to be as close as possible for best EMC. So in general, yes, it is a good idea to have that ground plane very close to the signal, and bringing it closer does reduce EMI susceptibility, and it works in reverse as well. It does help reduce radiated emissions from a signal on that interconnect. It doesn't mean that SI is necessarily better because SI depends on a number of factors, and when we talk about signal integrity, we could be talking about multiple different things. So let's dig into the details just a bit and we can see what I mean. So I'll address the first part of the question first, which is all about the relationship between the capacitance that you're trying to drive versus the rise time of the signal that you actually inject into the interconnect. So let's just suppose I have a transmitting component, we'll call it TX. It's connected to a trace, and then here I have a receiving component, RX, okay? And then I have a ground plane underneath these, and then there is some distance here, we'll call this D, okay? Now, this trace does have some capacitance, and the capacitance of this trace is roughly inversely proportional to D. Now, it's not an exact 1/D relationship. There's actually some complex equations that are used to understand the relationship between the impedance and the size of the trace and the distance to ground, and then of course the decay value of this insulator. But you can roughly approximate the trace capacitance to be 1/, this distance between the trace and ground. So what would happen to the trace capacitance if we were to just move the ground plane closer to the trace? Well, then obviously I would be making D smaller, and so if I make D smaller, then I would expect the trace capacitance to go up. So the trace capacitance here would go up. Now the other thing that would happen is the trace has some inductance, and the inductance would also go down because I'm enclosing a smaller area between this trace and the ground plane for its return current. So remember, the characteristic impedance of this trace, Z sub 0, is equal to square root of L over C. Now this is in the lossless case, so we're ignoring things like skin effect and dielectric loss. Just in this lossless case, we'll look at the case here where we have square root of L over C. If C goes up and L goes down, then when I move this ground plane closer to the trace, then the characteristic impedance also goes down. Pretty simple. Now, because this trace capacitance went up, it is true that the rise time would also increase. Now, remember here, you're not just driving a trace, you're also driving a load capacitance. And the load capacitance could vary anywhere from, for example, a few picofarads for very advanced, very small buffers, all the way up to tens of picofarads for older components. So let's just suppose here, as an example, the load capacitance that I'm trying to drive is 50 picofarads, okay? And let's say that this trace capacitance here is 3 picofarads per inch. Well, it's entirely possible that, yes, you do bring the ground plane closer to the trace, and it does increase the trace capacitance a bit. However, this may not be a very large impact on the total capacitance that you're trying to drive, because the total capacitance that you're trying to drive is equal to the load capacitance plus the total capacitance of the trace, which is CT multiplied by the length of the trace. Now remember, trace capacitances are in capacitance per unit length, and so that's why we have to multiply by the length of the trace. But now remember, we brought the ground plane closer, and that reduced the impedance. and you brought up high-speed lines. Now, for the case of high-speed lines, this is important. Normally with high-speed lines, we actually want to maintain the impedance to be constant, even if we move this ground plane. Well, if we move the ground plane closer, how do we make the impedance constant? We have to compensate for this increase in the trace and capacitance by reducing the width of the trace. And so, if we reduce the width of the trace, we take W and make it smaller, we then restore this trace capacitance to the same value. And so that's the thing about trace capacitance and trace inductance. It doesn't matter if the ground is close or far. For a fixed value of the dielectric constant, the trace capacitance and inductance are going to be the same value if they have the ground closer or ground farther away. Now the same thing applies with differential pairs. Here with differential pairs, we don't just have a self-inductance and a self-capacitance, we have a mutual inductance and a mutual capacitance between them. Now these terms will also change if I bring the ground plane closer to the traces. So that's something else that we'll have to discuss here in the next section when we look more at EMI and SI. But for now, just remember, even if you bring this ground plane closer to a trace, we always try to have the same trace impedance with high-speed links, and that's why the width of the trace has to go down to compensate, and that roughly keeps the trace capacitance constant. So in those cases, the total capacitance that you're trying to drive is essentially the same. Now, the rest of this question from Albert relates to the interaction between two traces, or the interaction between a trace and some other source of electromagnetic energy that may not be located on the PCB. So let's again look at this with a TX and RX component, but we'll look at it from the overhead view. Here I have my TX component, I have a trace being routed out, I have another trace over here being routed out, and then these connect to an RX component over here. Label it RX. And then there's some spacing between these two traces. So these traces each have a width, and then they have a spacing value between them. Now, because these traces are able to interact with each other through the electric field and the magnetic field, they have a mutual inductance and they have a mutual capacitance. And it is these two terms, as well as the self-capacitance and the self-inductance, that determine the amount of crosstalk between the two traces. Now, what if there's some other source of electromagnetic energy that is maybe not located on the PCB? Well, you could model the amount of signal injected into one of these two traces, also using a mutual capacitance or a mutual inductance, if you like. But typically when we bring these up, we're bringing them up because we want to talk about differential impedance, or we're talking about crosstalk between two traces. So now, what happens to crosstalk if we were to then take that ground plane and move it closer to these two traces without changing the width and without changing the spacing? Well, if all we did was move the ground plane closer to these traces and we didn't change the width and we didn't change the spacing, then bringing the ground closer will reduce both of these parasitics. LM and CM will go down, okay? So this would reduce the amount of crosstalk between them. It would also reduce the susceptibility to external EMI, and then this works in reverse as well. It also reduces the amount of noise that these two traces generate and then radiate away from the PCB. Now remember, because we brought the ground closer, we also reduced the characteristic impedance of each of these traces. But remember, if we're dealing with high-speed links and the impedance of these links matters, how do we restore that impedance to the target value? Well, our width also has to go down. Now again, if all we did was decrease the width and then we left the positioning of these two traces the same, that means the spacing would have to go up. And you can just see this from the overhead view. If I take this trace and I make it skinnier, I take this trace and I make it skinnier, the edge-to-edge distance between these two traces has to increase, okay? So that also helps to decrease crosstalk. But what if I follow one of these rules of thumb and I also change the spacing so that it compensates for that change in width, and I maintain this constant ratio of spacing to width? For example, I set my spacing to 3W. This is a common rule of thumb. What's going to happen to crosstalk? Well, I think you might intuitively expect that the crosstalk either won't change or it's still going to go down. But what actually happens is as you bring that ground plane closer and you decrease the width of the traces, and then you maintain this constant multiple of width as your spacing value, you're going to force those traces closer and closer together, and your crosstalk will start to go up. And this is something called crosstalk penalty. So the crosstalk penalty arises because you're forcing those traces closer together by maintaining this constant ratio. Now let's just suppose for a moment that we have a situation where we're routing traces like this. We started out with a value of S equals, let's say 1.5 W, okay? So for example, we started with 6 mil trace, 6 mil trace, and then our edge-to-edge spacing was 9 mils, okay? If we bring the ground closer, we're gonna start to see an increase in crosstalk if we maintain this constant spacing value, okay? Now, in order to compensate for that higher crosstalk, we may need to increase this spacing. So instead of having a 1.5, maybe we need to have a 2.5, for example, spacing between our traces. So now instead of that original value of 1.5 times the width, it's now 2.5 times the width, okay? So that can overcome the crosstalk penalty. Now this is something I've been talking about quite a bit at various industry conferences, and it's all about signal integrity on thin PCB layers. Because once you get to really thin layers where you have these traces very close together, you start to notice a lot of additional crosstalk. And the only way to overcome that crosstalk penalty is to increase this spacing value as a multiple of the trace width. So I'll definitely be doing more videos about this and talking about it on my channel. If you're watching this, make sure to hit that subscribe button. You'll be able to keep up with all of that information as I put it out. Thanks for watching this video, everybody. I always love getting great questions like this. And of course, you can leave a question in the comments section. And if it's a good one, it just might end up in one of these videos. Thanks again, everybody, and I'll see you next time.